The most frustrating testing experience: when your tests pass locally but fail in production because they never actually touched the network. We'll demonstrate FastMCP's in-memory testing pattern that lets you verify real network behavior without leaving your process. You'll see how to spin up a server, make actual client calls, and validate responses, all in a single test file with zero deployment overhead.
From FastMCP, import FastMCP, client. Hash create your server. Server equals FastMCP, weather server. At server tool. Def get temperature city, SDR, dict. Get current temperature for a city. Temps equals NYC, 72 LA, 85 Chicago, 68. Return city, city temp, temps get city 70. Async def test weather operations. Hash pass server directly, no deployment needed. Async with client, server as client. Result equals await client, call tool, get temperature, city, NYC. Assert result data equals city, NYC, temp, 72.
This demonstrates in-memory testing with direct server-client communication, a pattern that eliminates network overhead during unit testing. The approach treats servers as first-class Python objects that can be instantiated and tested without deployment, while clients connect directly to these in-process instances. What makes this distinctive is its ability to test the complete RPC stack, from tool registration to response handling. Let's break it down line by line.
From FastMCP, import FastMCP, client.
Imports FastMCP for creating AI callable tool servers and client for local testing without deployment. These are the core components for defining and testing MCP-compatible tools in Python.
Hash create your server. Server equals FastMCP, weather server.
Instantiates the FastMCP server as the central orchestrator for AI callable tools. The weather server identifier names this specific toolset, enabling clear separation when multiple servers run concurrently. This is the entry point for defining all available tools and their execution context.
At server tool. Def get temperature city, SDR, dict. Get current temperature for a city.
The @server tool decorator registers this function as an AI callable tool in FastMCP. The type hints and docstring automatically generate the tool's schema, defining the input-output contract for AI models. This is the core pattern for exposing Python functions to AI systems. The decorator handles serialization, validation, and schema generation behind the scenes.
Temps equals NYC, 72 LA, 85 Chicago, 68.
This hard-coded dictionary serves as a mock data store for city temperatures. It provides predictable test responses, eliminating external API dependencies during development and testing. The get, with default value, handles missing cities gracefully, preventing key errors.
Return city, city temp, temps get city 70.
This returns a structured response with the city name and its temperature. The get city 70 provides a fallback value of 70 for unknown cities, ensuring the tool always returns valid data even with missing inputs.
Async def test weather operations.
This defines an async test function for FastMCP operations. It verifies the server's tool execution without requiring a separate deployment, enabling fast iteration during development. The async prefix allows using await for client calls within the test.
Hash pass server directly, no deployment needed. Async with client, server as client.
This uses FastMCP's context manager pattern for testing. The async with block creates a temporary client connection to the in-memory server, eliminating the need for actual deployment during tests. It automatically handles connection cleanup when the block exits, preventing resource leaks.
Result equals await client. Call tool, get temperature. City, NYC.
This invokes the getTemperature tool remotely through the client. The dictionary argument, city, NYC, becomes the tool's input parameters, and await handles the async response. This demonstrates the exact client-side call pattern your AI would use when executing the tool.
Assert result data equals city, NYC, temp, 72.
This assertion verifies the tool returned the expected data structure. It ensures the FastMCP client-server communication works correctly, catching any serialization or protocol errors early. This is the standard pattern for testing tool outputs in MCP systems. In-memory testing, pattern. FastMCP's in-memory transport eliminates network overhead by running the full MCP protocol within a single Python process, enabling deterministic tests that execute in milliseconds. The client connects directly to the server instance, bypassing deployment entirely, yet still validates the complete protocol implementation. This approach makes your tests both lightning fast and production faithful. Missing the async with context manager will silently leak connections and resources during testing. The same test pattern works for both simple tools and complex server integrations.
The transport that disappears tests everything.